the wavelength lambda associated with a moving particle depends on its mass, m, velocity of motion v, and Planck's constant h. Now Planck's constant has its units to be provided, and these are kg meter squared per second. Show dimensionally that lambda is direct proportional to the Planck's constant and inversely proportional to the momentum, which is mass times velocity. So this is Namakando Academy YouTube channel. Please consider subscribing, liking, and sharing our content. Alright, so let's get started. So this is a question based on derivation, but we've been given the final result. So we should make sure that whatever we do, we should strive hard to make sure that we obtain what we've been given in the problem. So let's look at the statement we have. The statement says that the wavelength which is associated with the moving particle depends on three parameters, or other physical quantities, which are mass, velocity, and the Planck's constant. So mathematically presenting this will mean that wavelength, so looking at our solution, wavelength depending on the other physical quantity mean that is direct proportional. So we'll use this symbol for direct proportionality, and what we are given is mass. Now we don't know if it has an exponent, so we raise it to the power a, v to the power b, and Planck's constant h to the power c. Wavelength has its dimensions, it's still length, so the dimensions are L. And so as to accommodate mass and t to appear in the equation, we'll assign the exponent for mass to be a 0, L it is a 1, t to be a 0. Alright, so this is our left hand side, so we'll do the substitution. Like this. Then this is direct proportional to. So I'm not changing this to an equal sign because what we've been given is simply just like this. Then mass is m to the power a, and v is L t to the power negative 1 raised to the power of b. H, which is a Planck's constant, has its units to be provided, which are kg for mass, meter squared for area, which is just L squared, then per second, so we just say t power negative 1, and this has the exponent of c. So this is m naught L to the power 1 t to the power 0, like this, direct proportional to m to the power a. So distribute b inside, we'll get L to the power b t to the power negative b, multiplying with m to the power c, L to the power 2c, and t to the power negative c, like this. Okay, so now left hand side to be maintained. And this is proportional to, so we have m. Now there's mass multiplying with mass, so we add the powers. So this is a plus c. Then come to L, which has b here. Then there it has 2c, so we add these two since they're multiplying. Then we have t, the power negative b, then minus c, like that. So according to the principle of homogeneity, left is the same as right. So meaning that for m, on the left, since I have a 0, and on the right I have a plus c, so I'll say a plus c is equals to 0. Then b plus 2c for L is equals to 1. And for t, I have negative b minus c on my right, and on the left it is equals to 0. So these two are equal. So from this which we have, we simply have three equations which can be solved simultaneously. Now if we look at the second, so we're going to combine these two and solve them simultaneously. So I have negative b minus c equals to 0. So here we're going to use elimination. The sign we're using is a plus. Okay, so b plus negative b is a 0, so mean that we have 2c minus c, which is just a c, and this gives us a 1. Hope you are good with mathematics for you to be able to solve this. So c is done. We now find b. So we can choose between the first and the second. So the best is the second, which is negative b. Push negative c, the other side becomes c, and b will be equals to negative c, which means that b is equals to negative 1. Right. Now we go back to the other equation which has a. So this one is a plus c equals to 0. So from here, you make a subject of the formula. So what you do is you say that a will be equals to negative c. And since you know what c is, it is 1, so mean that our a will be negative 1. Now remember our equation is presented like this. So let's substitute the respective exponents or other values for a, b, and c. So we'll have our lambda to be proportional to m to the power negative 1, v to the power negative 1, and h to the power 1. So this comes out to be, here h is raised to a positive exponent, so it will be the numerator, then these ones will be denominators like this, and we've proven